In this video, I want to talk about some different ways to make a current source using bipolar technology. Now let's consider the ideal current source. So let's say that this is a current source, and I'm going to ground one terminal. This will be the second terminal. This will have some voltage V at this terminal. And let's say that this current in this current source is equal to 1 milliamp. Now, an ideal current source will have a current versus voltage relationship where this is current and this is my voltage. That is very flat. So ideally this will just be a very constant current. So let's consider using a bipolar transistor how we can make a current source. So let's say I have an NPN bipolar transistor, and let's set the base voltage at 2 volts. Let's connect an emitter resistor to ground, and we want to produce a constant current in this collector terminal. So recall from previous videos that the base emitter drop on a typical NPN transistor is on the order of 0.7 volts, plus or minus a little bit. But just a rule of thumb, approximately 0.7 volts. And let's say I want to set this current source for about a milliamp of current. So if I calculate the voltage at the emitter, subtracting 0.7 from 2 volts at the base, I get my emitter voltage of 1.3 volts. So if I set this resistor to 1.3 K, I get a current flow in the emitter, and if my base current is very small, my collector current will be 1 milliamp. Now this current source will be a little less than ideal. Let's plot my current versus voltage, and this is the voltage at the collector terminal and the current in the collector. So the key thing is that the voltage on this current source is limited. Now there's a junction diode in this base collector region that I never ever want to forward bias. So this will act as a fairly decent current source as long as the forward drop on this diode does not cause conduction in this collector to base diode. And so I could go as low as, say, 1.6 volts for the operation of this current source. And that would give me 0.4 volts forward bias of this diode, which may be acceptable. So this current source is going to have a range, and it can operate above 1.6 volts and provide a milliamp of current approximately. So let's say this is 1 milliamp, and there'll be some variation. Maybe my base voltage is not a perfect 2 volts, so that may vary up and down, and that'll change my current. There's a temperature dependence on this base emitter voltage. At high temperature, the base emitter voltage will shrink a little bit. Perhaps my resistor at higher temperature, perhaps it'll increase a little bit. So there's some variation that's unavoidable. Won't be a perfect milliamp. And I cannot really operate in this region here because I would forward bias this base to collector junction diode. So let's consider some other ways we might do this current source in bipolar technology. Here I have two identical NPN transistors where the base and collector nodes are connected together, and I have a resistor connected to plus 5 volts that supplies 1 milliamp of current to these transistors. And the key thing is that these transistors are identical. So that means that they have equal amounts of current flowing in the emitter. So this current is 0.5 milliamps, and this current in this emitter is 0.5 milliamps. Let's say that I make a change to the circuit. I'm going to remove this connection here. And I'm going to connect this collector over to a battery. And I'm going to set my battery voltage at 0.7 volts. And this node here will also be about 0.7 volts since this transistor behaves like a diode. Under this situation, my 1 milliamp will essentially flow through the emitter of the NPN transistor on the left. So the current here will be 1 milliamp. And I'm going to say that I have a very high beta transistor. In fact, I'm going to make a simplification. I'm going to say that the beta of these transistors is equal to infinity. In that case, the current flowing in this base terminal is 0. The current flowing in this base terminal is 0. And of course, that's not a valid assumption. We never have betas equal to infinity. But it turns out it really doesn't make too much difference in this circuit. So we'll just make that simplifying assumption. So since these transistors are identical, and since they have the same base to emitter voltage, they have the same emitter current. So the current flowing in the emitter of the transistor on the right will also be 1 milliamp. So if I were to change the voltage at the collector from 0.7 volts to different voltage values, let me erase this and say I'm going to call this voltage V. So let's plot the current versus voltage characteristics. So this is my current axis. This is my voltage axis. This is my V. And the current here, I, we'll plot on this axis, I. And we, at V equals 0.7 volts, let's say that that's about here, the currents will be exactly equal. The bias conditions are the same on both NPN transistors. So I would expect about 1 milliamp. Now, again, I have to be concerned about forward biasing the diode in this junction. But since my base voltage is sitting at 0.7, I can go pretty low. I could probably go down to 0.3 volts or so and still be operating as a current source. So this can go to a much, much lower voltage than the previous current source. And as I increase voltage and I plot the current, this current's going to have some slope due to the characteristics of this NPN transistor. So it's not an ideal current source. It has an advantage that I can go down to perhaps 0.3 volts or so, have to avoid this region of operation. But not too bad of a current source, and it's very useful in many different applications. But let's make a change to the circuit, and we'll see if we can improve it a little bit. Let me erase some things here. Let me erase this. Clean this up a little bit. And let's add another, whoops, let me change colors, do an undo. Let's add another NPN transistor here. We'll connect this base over to this collector. We'll round this emitter. And over here, we'll do the same. We'll add another NPN transistor. We'll ground the emitter. And we'll connect this base over to this connection over here. So let's analyze what happens in this situation. Let me just clean this up a little bit here. Get rid of our diode. Now we know that the diode drops about 0.7 volts. So I have 0.7 volts at this node. I have 1.4 volts at this node. And I can adjust this resistor value to still provide 1 milliamp flowing in this resistor. Now in this situation, this transistor is identical to this transistor. They have exactly the same geometry. And let me change colors. I have 1 milliamp essentially flowing in this chain here. Since these transistors are identical, I have 1 milliamp flowing in this transistor. And the key thing here is if I look at my voltage, I have 0 volts here, I have 0.7, I have 1.4 volts here, because every transistor, every base emitter voltage drop is 0.7 volts. So if I have 1.4 volts here, I have 0.7 volts here. And that 0.7 volts is going to remain rather constant. So the key thing is that the operating point on this transistor is at a point. It's not going to change very much. I can change this voltage here quite a bit. But the operating point on this transistor here that controls the current doesn't change much. So in this case, the current will be very flat. It won't have this high slope here. But my operating voltage will be not as good. So again, I have this junction diode here that I do not want to forward bias. If my base voltage is sitting at 1.4, I could go down to perhaps around 1.0 volts or so here. So this current source, let me change colors, will have a range, operating range here of about 1 volt. I don't want to operate it in this range. So I've lost some voltage margin on my current source, but I've gained a very constant current source. And sometimes that might be useful. Here I have a previous current source, but I've added one more NPN transistor. And let's say that instead of 1 milliamp flowing in this resistor, I'm going to decrease that a little bit and design it for 1/2 milliamp. Now what if I do not make these transistors identical? Let's say that I have one, or this half milliamp flowing in this emitter, but I'm going to adjust the emitter of this middle NPN to be larger by a factor of 2. So if I draw the actual physical layout of this emitter at the left, it could perhaps look like this, a perfect square, and have a certain area. Now the transistor in the middle, I want to have an emitter with twice the area. So one way is I could lay out 2 identical emitters. So the area of these 2 emitters is twice that of the area of the transistor at the left. So because of that, I have twice the current flowing in this base emitter junction because my bias levels are the same for the transistor at the left and the center transistor. So that gives me a current source here with twice the current, or 1 milliamp. Now let's presume that I want to make the emitter on the transistor at the right to be 4 times. So if this is 1x emitter size, this is 2x emitter size, I want to make this 4x emitter size. And in that case, I have 4 times the current flowing as the transistor on the left. In that case, I've made a current source that runs 2 milliamps of current. So you can see by adjusting the base emitter area of these NPN transistors, I can create many different transistors here with different current properties.